in finite element analysis. Various steps involved in finite element analysis. Actually, we have 7 steps because in classical approach also I told the 7 steps. There also we follow the same 7 steps, absolutely no change, with of course a different procedure. So first step, step 1, that is called discretization. Discretization. That is called discretization. So that is given a structure or given a body or given a domain. You divide that domain into smaller, finer elements, and these elements are interconnected at finite number of points called nodes or joints, and unknowns are treated at these joints. So that is called discretization. So as I did in that finite element principle, so discretization. So in this step, the given structure or body or domain or body is divided into a number of small finite elements, maybe one-dimensional or two-dimensional or three-dimensional, depending upon the problem. Three-dimensional elements, small 1, 2, 3. Because already I told in classical approach also, one-dimensional problem is that problem which are made out of only by one-dimensional members, that is line members. Two-dimensional problems are those problems which are made out of area members, area elements. Three-dimensional members are those which are made of three-dimensional members or elements. Same approach. Actually, there is nothing in classical object. There also we did the same thing. So here it's a different way I'm telling. That's all. So in the first step, we have to divide that into small and finite elements, 1, 2 or 3 dimensional, which are interconnected, at finite number of points, are interconnected at finite number of points called nodes or joints. Nodes or joints. Elements or members. Nodes or joints. The unknowns to be determined, or the unknowns to be determined. What are the unknowns to be determined generally? In our structural mechanics problem, what we are dealing here, computational mechanics. In mechanics problem, the unknown is mainly displacement. Because when the application of load is there, so it results in displacement or deformation. There are 2 types of deformation you do, translation and rotation. That's all. 2 types of deformation, angular deformation or linear deformation. So those deformation, the unknown deformations, you have to determine in global coordinates only, because loads are all in global coordinates. Of course, the loads will be in any direction, but for analysis purpose, we resolve all those loads along three fundamental orthogonal global coordinate system, x, y, z. So you are resolving into x, y, z direction in three directions, and these three direction loads will result in three displacements in general. Those three displacements we call as u, v, w. That you have. Displacement in x direction is called u, y direction v, z direction w. So the unknowns to be determined, that is mainly displacements, in mechanics problem, mainly displacements in mechanics problems, or velocity in fluid flow problems. So here it is, we are dealing with only displacements in mechanics problem. So unknowns are mainly displacements in mechanics problems are selected at these nodal points. That is discretization. First step. Generally, discretization, we have to remember, already I told mesh refinement. So that is one type. That is mainly on the selection of loads. So that you can take care. Other points, we have to number these nodes, we have to or joints. How to number these nodes? We have to number these nodes, not arbitrarily you can number it, but since we are using the computer, we have to just save the storage space of the computer. So since storage of space is essential, we have to number it in certain fashion, because especially when we are solving the equation, we are using large number of space and that to be reduced. So fortunately, all our stiffness matrix, that is, the general equation P is equal to K into D. In that K matrix, D is the unknown. K matrix, it is a banded matrix. Banded matrix means some of the elements of that matrix becomes zero. You have seen, I determined in the earlier calculation, most of them are zero. In rotation matrix, you have seen some matrix, the elements are becoming zero. So like that. So in this stiffness matrix, if you find that you can form a band above which all elements are zero, those elements you can just ignore and take out only the elements which are existing within the band, that is banded matrix. So the band width, within the band width, what are the elements which are existing, only that you can utilize for the analysis, which saves the storage space in the computer. So while dividing, discretizing this, so you have to discretize and number the nodes in such a way that the half band width, it becomes minimum. That is the extra care you have to take it. This aspect, I will just explain here itself. That also will be taken care. Because all these are there in your unit 2, aspect ratio, bandwidth, and all those things that way. I want to cover it off fully. So, while numbering the nodes during discretization, we have to see that the semi-bandwidth semi-bandwidth, semi-bandwidth is minimum. Semi-bandwidth is minimum. Also, we have to see that the aspect ratio, is less than 3. So these are the two aspects which we have to take care while discretizing the element. One is that refinement. That also we have to take care. Refinement means we have to go for more number of divisions or measures, or we have to go for more number of nodes. That is H refinement and P refinement. Either we can adopt that along with these two aspects, that is semi-bandwidth and aspect ratio, that we have to take care while discretizing in the form of measures the entire domain. Right? So the aspect ratio is defined as the ratio between largest size of element to smaller size. That's all, a simple definition. Aspect ratio is defined as the ratio between larger size to smaller size. Provided if you go for two-dimensional elements, I am talking about these two, because it can be divided into one-dimensional, 2, 3 I told. Especially when you go for two-dimensional idealization or discretization, there are 2 dimensions. So that 2 dimensions you have to divide into number of parts and number of nodes. As well as you have to take size, whether they are of equal size or different size. So the restriction is put in the division, in taking care in discretization. You have to take care that ratio of the larger side of the one element and shorter side of the element should be less than 3. And also the semi-bandwidth, which affects the storage, which increases the storage capacity, which reduces the storage capacity, so that semi-bandwidth should be minimum. You have to calculate the semi-bandwidth well before, that is by numbering the node itself. So that aspect I will explain. For example, consider a two-dimensional slab or plate, thin plate. I am talking about thin plate because I told you a two-dimensional structure is one wherein one dimension is small when compared to 2 others. So that's why I am taking thin. Thin means only thickness. It is small when compared to other 2. Ratio of other 2 is only I am referring. That's why I am taking the example of a thin plate analysis, slab analysis or in that way. Consider a thin plate which is divided into number of elements as below. So you consider a thin plate of rectangular thin plate of 5 meters and 3 meters. So you divide this into small square elements like that. That is 1 meter by 1 meter square. So you divide that rectangular plate into small square elements like this, 1 meter by 1 meter square. Now, aspect ratio of the element is 1 by 1. So it is perfectly all right, less than 3. So when dividing, it can be anything. You can go for either 2 divisions here, 5 divisions here. So then aspect ratio will be different. But you divide in such a way that it is always less than 3. So that's up to you. This is what that aspect ratio means. Now, numbering of nodes, calculation of bandwidth. So you have to number this. I have intentionally taken different sizes, 5 meter. If they are of same size, well, it doesn't matter. Is square size. If you have different, but of course it depends upon again division. You can go for less number of divisions on one side. So that is always there, right? So only with respect to the element I am talking about. We are all talking about element properties, this aspect ratio number. So you can number it in 2 fashions, right? So numbering of nodes can be of 2 types. One type, you can number it vertical wise, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. You can number in this fashion. Or you can number in a different way. So you can number along lengthwise, sequentially along the length, or along with this 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Number of nodes has to be same in both cases. Only numbering way is different. In this way I have numbered the nodes in the vertical direction. In this way I have numbered in horizontal direction. You can number it in any fashion. There is no, you can go like this and again come like this, is any fashion. So only my aim is to explain how to find this semi-bandwidth. It has to be minimum while numbering. So in this case, case 1 of numbering, case 2 of numbering. In case 1, in this case 1 numbering system. In case 1 numbering scheme. semi-bandwidth. I told you it has to be, semi-bandwidth has to be minimum. That's what I am explaining now. In this case, semi-bandwidth is given by the formula B is equal to 2D plus 1 or D plus 1 into N, where D is semi-bandwidth, where B is called semi-bandwidth, and E equals maximum difference. Maximum difference between two adjacent nodes. Two adjacent nodes which are interconnected. So adjacent nodes, and N is degree of freedom at each node. That's the formula we have, right? For scheme 1, right? What is the maximum difference between the adjacent nodes? If you observe, the maximum difference here it is 4, here 4, here it is 1, here it is 1, here it is 1, here it is 4, right? And the maximum difference you have observed is 4. So, in scheme 1, in case 1 number in scheme, so here D equals 4. Correct? Huh? So let us say the degree of freedom is 2 at each node. You assume, because I told thin plate. Right? So, thin plate virtually there will be 3 mx, my, and theta x, theta y, and w. So, say we will take all those. So, assuming 3 degrees of freedom, theta x, theta y, and w, one vertical deflection, another 2 rotation, because it's a plane figure. 3 degrees of freedom, n equals 3 freedom. Assuming n 3 degrees of freedom, semi-bandwidth will be 4 plus 1 into 3, 15. Right? Whereas, for scheme, for case 2, the numbering scheme 3, you observe. Difference between here it is 1, 1, 1, 1. Here 6, 6, 6. So it is 6. So here for case 2, the maximum difference is 6. Therefore, your P will be 6 plus 1 into 3, that is 21. So naturally, this numbering scheme is preferable. You have the number vertically. It is advantageous. It will reduce my computer storage capacity. It is advantageous. So these are the aspects you have to remember while discretization of the domain. First step, I am talking about first step now. First step of finite element procedure. Whereas in classical approach, first step was directly taking the data as it is. But here, you have division itself. You have to do in such a way which has taken care of all these aspects. Aspect ratio, then semi-bandwidth, and also that mesh refinements, that is going for more number of things, this entire aspect, which is there in your Unit 2. Unit 2 is completely about this. Nothing else than that. No problems, nothing, only this theory aspect. Nothing. Next, we will go for step 2 of finite element analysis. Next, step 2. In step 1, all these aspects. And also how to select nodes. So you have to select nodes at preferably under the nodal points, under the load points, and also wherever the varied cross-section is there, the material property changes. All those locations if you take automatically, that solves the problem. Whereas in classical approach, we cannot solve. We say if it is non-prismatic, it cannot be solved. I will say scatter, because formation of stiffness matrices becomes difficult. So here, that the selection of just node, you will take care of all those. I hope I made the things clear. In step 2, displacement model. Displacement model. That is step 2 of finite element analysis. Because I told you we are selecting at each node the unknown of the problem. The unknown of the problem is called field variable. In structural mechanics, the field variable, as I already told, it is displacement, wasted. Right? And of course, slope is first partial derivative of the displacement. That's called slope. Displacement model. So, the unknowns are in that step, explain the steps, indicate the steps, then I will take all these individually again. What is the displacement model and all. Step 2 is the displacement model. I will highlight what is that contains. So, we at each nodal point we select the unknown displacements, which is generally unknown variables called field variables. Field variable, which is generally a displacement in structural mechanics problem. In structural mechanics problem. So at each nodal point we select a known variable called field variable as general, which is generally the displacement in structural mechanics problems. That is that. So we have to experiment in the form of a polynomial satisfying 3. Formation of element properties. And step 4, formulation of element equations. Then step 5, finding global structure formulation, global structure equations. Step 6, solution of equations, global equations. And last, step 7. Evaluating N forces or stresses. That's all the 7 steps, similar to whatever we have done. So these are the only steps I have to explain. Step 2, step 3, how to get the displacement model, how to get the element property, that's Kn, mainly measurement matrix, stiffness matrix. And of course, how to form the global form that we know. These also we have done in classical code. So in the next class, you can just do selection of this model. And here in your discretization, there is one more aspect, type of problems. So that I will indicate here itself. And so in addition to numbering of nodes and also the aspect ratio, so those two, we have to just remember what is known as type of or classification, classification of problems. So in structural mechanics problems, one is, so if a governing differential equations, if the governing differential equation of a problem, if the governing differential equation of a problem involves nth order of differential nth order derivative if it involves nth order derivative of the field variable. I have explained what is the field variable already. If the equation, governing equation, it contains nth order derivative, then the problem, if the governing differential involves nth order derivative, then it is called, then it is called C n minus 1 type of problem. It is called C n minus 1 less than that largest derivative. If the problem involves if the problem contains nth order derivative. Okay. So for example, for a bar problem, for a bar or plus problem, the governing differential equation is d by dx of AE du by dx is equal to 0. Here, this contains highest derivative as du by dx. This second derivative anyway is 0. So this contains highest order as 1, differential as 1 first order. So it is called C0 type of problem. This is called C0 type problem. Similarly, for a big, okay, these are the things we have. And flat problem we don't have anywhere, only if I told these things, okay. For a big problem, the equation is d2 by dx square of ei d2 by dx square is equal to wx load. And here d4 by dx4 equals wx. This contains a higher order 2. Because this is just second derivative has to be 0, the slope, because it has slope. So here, this is called C1 type of problem. This is called C1 type problem. Like a plate bending problem, you have a shell problem. It will be C3 type, C4 type, like that. You have different type of problem. This is another aspect which you should have. If you have a governing differential equation for a given problem. So this much information you should have before going further. In the next class, I will explain how to select a displacement, that is using polynomial already I have told, then how to get element property. So these two, if I explain, of course that completes your entire finite element approach. There is nothing much here. So these two I will explain in another class, in another number also. So I will close it. So